All right, we're back. This is Chapter 5 and 6 review, problem number 6, a very tricky fundamental theorem of calculus problem. First thing I'm going to go ahead and do here, well, the reason why it screams fundamental theorem is because we're going from 0 to a variable, taking a derivative with respect to that variable, where there's an integral that's with a different variable. But anyways, I'm going to go ahead and call y is equal to 0 to t squared, the integral of u to the fifth under the square root du. So I'm setting y equal to what's inside of here. And if I want to evaluate that, that means that what I'm looking for is dy dt. And so the problem is that with the fundamental theorem, it doesn't guarantee that you can go from 0 to a variable squared or cubed or under the root. It has to be a variable all by itself. So we're looking for a single variable up here, and we don't have one. It's t to the squared. So we need to do a substitution. So we're going to let v equal t squared. And then what we're going to do is we're going to figure out how are we going to find dy dt. Well, using the chain rule, dy dt can be evaluated by finding dy dv times dv dt. Because the dv's cancel in a sort of hypothetical way, and what you're left with is just dy dt. So this is the chain rule. Well, we can find dv dt because we know v equals t squared. So dv dt equals 2t. Took the derivative of our substitution. But what's dy dv? So this is dy dt. Well, let's go ahead. So if this is dy dt, and we establish that y equals this thing, right? So therefore dy dv must be the derivative with respect to v, right? Because this is dy dt. Derivative with respect to v, d dv of y. Y is this, right? I define this as y, and that's from 0 to t squared to the square root of u to the fifth du. And here's the caveat, is that because I did my substitution, wherever there's a t squared, I can replace it with a v. And so I can replace this up here with just a v. And then dv dt is, of course, we solve for that, it's 2t. And so now we've proven that this new expression is in fact equal to dy dt, which is what we want to solve for in the first place. And so now we can use the fundamental theorem on this chunk right here, because you'll notice that there's a separate variable that's in the integral, a single variable v that is in the upper bound with a constant in the lower bound, and we're taking the derivative with respect to that constant v. So in this arrangement, what you can do is you know that this integral is in fact going to equal, well, the derivative of this integral is going to in fact equal the square root of v to the fifth, because the derivative and the integral cancel out, and what you're left with is wherever there was a u to the fifth under the root, now we get a v to the fifth under the root. Alright, so that's this one evaluated times by 2t equals dy dt. Alright, so now what we're going to do is we're going to write v in a different method. Now something raised to the fifth power and under the square root could also be written as power 5 halves. Because the halves, power 1 half represents under the square root, and power 5 represents that it was raised to the power 5. Now, we don't want this in terms of v because we're looking for dy dt, but our substitution v equals t squared, we can put that back in. So if v equals t squared, and if we have a power raised to a power, then we just take those two powers and multiply together. 2 times 5 halves, 2 times 5 halves, the 2 cancels out, and you're just left with t to the power 5. So what we have here is t to the power 5 times 2t equals dy dt. And then we can finish up the problem now and multiply these two things together to find that dy dt equals 2t to the 6th. Alright, so that's the problem for today. It's a multiple step problem, But if you follow these steps, you should be able to answer every problem that's asked in the question. So I hope this was helpful. I gotta tell you, this problem is a lot easier to do if you don't use the fundamental theorem of calculus, and if you just do the work of taking the integral with respect to u, then plugging in your boundaries like you were evaluating a regular old integral, and then taking the derivative with respect to t. You're going to get to this answer. It's going to be less painful. There's going to be no substitutions. That's the way I did it the first video I shot, but I deleted that video because it wanted the problem done this way. I may post the easier way too. The problem is because it's a step-by-step problem, you can't do it the easier way. You have to do it the more, what would you call it? Well, the trickier way. You've got to do it this way because a step-by-step problem wants you to. But I'm going to go ahead and make another video on how you could get to the final answer a lot easier than this. So, anyways, I hope this video helps, and I'll see you next time.